Okay, so welcome to part 2 of the Schubert seminar with Professor Andrei Okounkov. Part 2 is about general flag manifolds.
Thanks. So this is, it will start by somehow completely unrelated to what I said before. So if I have a smooth, compact, stably complex manifold M, I can define a genus. But if I have a function psi, I can take a product of that function over all Chern roots of my manifold, integrate over a manifold. So this would be some number, which will be additive over disjoint sums and multiplicative over product. So it's, and in fact, factors through the complex cobordism ring of manifolds. Imagine this must be pretty familiar to people in the seminar. And if I have a compact group action, I can define a Ktheory cohomology, and that will take part in the, this will take, so when I will push that for, that push forward is the push, integration is push forward to a point. So if in the Ktheory cohomology, this will take values in Ktheory cohomology of a point. So in H invariant functions on the Lie algebra. And you can observe that by continuity or in many other ways, if you start, of course, if you start with a polynomial, you get a polynomial. But if you start with some other, say, analytic function, and you get with analytic function, and in the region of analyticity, that has to do with, so if you had a region of analyticity in the neighborhood of the Lie algebra of the maximal compact, for so you think of function of one variable as having to do with the group U1. And so if you had some function analytic in some neighborhood of Lie algebra there, you'll get a function analytic in some neighborhood of the Lie algebra compact form in for your Ktheory cohomology of a point. Somehow, I hope it's familiar in this context. And it works just the same in any somehow extraordinary cohomology theory, but we right now we want to do it in K-theory, Ktheory topological K-theory. And the only difference between the K-theory and cohomology is that the cohomology of a K-theory of a point, that looks like the group itself modulo the conjugation. So it looks slightly more nonlinear. It's like a torus modulo Weil group, as opposed to the Ktheory cohomology. In the ordinary cohomology, you get of course the Lie algebra modulo conjugation. It's like the Lie algebra of the torus modulo Weil group. And all of these objects we will denote by boldface L, boldface lambda with the corresponding subscripts, for the reason that this would be, we had some space lambda of parameters before, and this lambda will be exactly this, the lambda for the first half of the talk will be exactly the lambda for the second half of the talk. And in particular, this lambda of U1 is just really just the group law. I mean, you need every, there's a group law corresponding to cohomology theory, and that's the group law, the lambda of U1. Okay, so it's, in other words, concretely, in ordinary Ktheory cohomology, that would be the additive group of complex numbers, and in the K-theory version, that would be just the non-zero complex numbers with respect to multiplication. So central to our argument is the observation, which is, I don't know, like so many things go back to classics, but in this case, it's not, maybe not Langlands, but rather Atiyah, or maybe somebody before Atiyah. But anyway, stated very clearly by Atiyah, is that if I have a non-compact manifold, then the genus can sometimes be also defined, but with values in distribution. And that's entirely parallel to the fact that if I have, this is maybe a fact that goes back to Gilfant and Harishchandra, is that if I have an infinite dimensional representation, I'd like to define its character, then it's naturally a distribution rather than a function on a group, right? Because if I need some kind of test function on the group to get an operator which has a trace, and so then I can take the trace, and that's how distribution works, and that's exactly the same here. And since it's convenient for us to work in algebraic geometry setting, and the particularly convenient weakening of properness, which so Atiyah IT's conditions are some kind of transversal ellipticity. For us is the particular convenient weakening of properness is something called homological properness. It's already been used by many people, in particular Dan, HL. And so what is a cohomologically proper maybe quotient stack is so if I have a map from the quotient stack to the point, and this has this has a push forward on coherent sheaves. Namely, the coherent sheaves you take the ordinary push forward and together with taking invariance with respect to your group, and it has higher derived things. So like a hierarchy homology of that push forward, and this map H mod H to X mod H to the point is called homologically proper if it takes coherent sheaves to complexes of coherent sheaves. So maybe finite complexes of coherent sheaves. So, I mean, that's so then you can, and then that's somehow that's what we can work with. And this equivariant genera then have very natural extension to some distributions on smooth homologically proper stacks, and maybe the nice maybe you can throw in some derived stacks. And we don't need a general theory. All we need is the only DGAs we need for this are just the good old Kazul, Chevalier, Alderberg, and Czech complexes. So we didn't pursue any kind of general theory, but I'm sure it exists and would be probably interesting to study. And so for orbifals, there's a very interesting study now by John Pardon, and he, I think, was planning to, at least maybe pursuing or planning to pursue the case of like general derived stacks, not necessarily orbifals. But anyway, I have nothing to say. I'm just saying, in my transparency set is probably be interesting, and I guess also at least one person who does this sort of thing is John. So maybe more. I don't know. Maybe I'm not just aware of the literature here. So but for actual application, all we need is just some very simple things, some just Kazul complexes, Chevalier Alderberg complex, and the Czech complex. That's all we need. But and so back to the spectral problem. So we have this identification where I have this boldface symbols lambda from different parts of the talk, and the way we'll identify them is the following. Let Q, this is script Q, that is the image of the norm map on ideals of your field. So for a field in positive characteristic, that is really the subgroup generated by Q. Q is the number of element of your little q, and that's the subgroup of positive real numbers generated by Q, which is why we call it big script Q. But for reals, the image of the norm is everything. So that's the difference between characteristic 0 and characteristic positive characteristic. And so in this table, we will have, so what would be that lambda? We will denote by boldface lambda the dual group, so the homomorphism from this group Q to C star. And so in positive characteristic, that would be just C star itself. And so it'll be the curve corresponding to the K theory. And in 0 characteristic, that group of homomorphism, that's C, and it will correspond to cohomology. And correspondingly, we for any torus, we can form that group, the corresponding group lambda, and that would be just the good old lambda which we had before. This is where the spectrum lies. And so therefore, since now we examine this table, and we see that in terms of boldface lambda, which we now define uniformly in terms of group script Q, we at least have a way to topological interpretation of this Eisenstein distribution. And we would also need dependence on the field. And the dependence of the field works like this. It's So the completed zeta function, it actually satisfies, is really, so completed zeta function, I didn't define what it is, but it actually is, so the functional equation for completed zeta function relays S and 1 minus S. Just really relate, I mean, just equal. So zeta of S equals to zeta, oh, sorry, psi of S equals to psi of 1 minus S. And so in particular, psi has a pole both at 1, where zeta function has a pole, and at 0. So psi has 2 poles. So if we'd like to interpret psi as some equivariant genus, then it better be a genus with something 2-dimensional. And so because it's means something non-compact, in fact 2-dimensional, and the corresponding geometries you take just basically C2, which I think of that as a quotient of T star C1 divided by C star squared. So they take that stack, and we would like, so this is, and it's C star equivariant genus. We would like to be psi of F. You can always achieve that. So you can always find a genus such that this is true. And so this is how you bring independence on the field. And so now, right. So yeah, there's a remark which I don't know if you're willing to accept it now, or we can take it later. You can, in the positive characteristic case, there's a very nice explanation what this genus is in terms of some sort of derived scheme structure. Maybe I'll come back to this remark later in the talk. And then I'll say, so that the spectral decomposition, now here's the kind of 2 main results. The spectral decomposition that we would the spectral decomposition in the length in this spectral problem, that's a consequence of the 2 following results. So first says that this distribution, the Langlands defines some distribution, and we say that distribution is really just the genus of this T star of, you take Langlands dual things and you take this G mod B on both 2 sides and take T star of that. And since you have division by B Langlands on 2 sides, this lives over point mod BL on 2 sides. And in particular, that lives over point mod AL on 2 sides. And so this is a distribution on 2 copies of lambda of AL. And the stack is not something. The stack is not anything scary. It's T star, and you have a quotient on 2 sides, which means, what does it mean to have a T star of a quotient? It means you have a like some kind of Kazul complex for the moment map, and you also have when you take the quotient by B on 2 sides, means there will be first some Chevalier-Eilenberg complex for the unipotent radical of B, and then we'll take invariance with respect to the torus. So it's not, it's maybe, the cute, I don't know, the one of the easiest stacks you can ever study. And like I said, you take the genus, appropriate genus of this object, and that would be that this genus is non-compact, is defined as a distribution, and that distribution is the Langlands distribution. And so right, so that's first. And right, and since this is T star to something, this lives in the world of T stars, and so in particular, this really depends only on the zeta function and not on the particular genus, because so this is T star to something, and so its genus is going to be consist of not just, you never have to evaluate your genus of C. You will always need to only evaluate the genus of T star of C, and the genus of T star of C, we decided this is the zeta function, completed zeta function of our field. So it doesn't really depend on there are choices of there are many possible psi's that represent the same C here, but that choice that doesn't depend on the choices you make here. So that's one result, and the second result is that Well, this is T star to, this is basically T star to G mod B, right? For T star G mod B, we have the Springer, whatever, Grothendieck-Springer map to the nilpotent elements, and accordingly we can decompose this space. So this is that space. Did I didn't know that? Right, I didn't know that the script T, this space, this T star to this quotient on two sides. And if you think about what the Springer resolution does, then what you're going to get is the following. You take, first of all, you take a sum over all nilpotent elements up to conjugation. And then for every nilpotent element, you get the 2 copies of the Springer fiber, because we take B quotients on both sides. Get 2 copies of the Springer fiber. You get the Thom space of the embedding of 0 into the slice at your dual Lie algebra at the corresponding point. It's just, that's just a linear space. It means a Thom space. It's a Thom space of embedding a point into a vector space. And then you mod out by, and then you take the quotient by the centralizer. And this is somehow this is more or less obvious if you think about it again in terms of Springer resolution. And what I'd like to say in this transparency, that this is the group, the maximal compact subgroup in the centralizer arises is just really that there's a maximal compact subgroup of the centralizer of a nilpotent element E, and the integration along the Springer fibers that determines the spectral projection, and the parts about the slice and the unipotent radical of this centralizer, they contribute to the spectral measure. So maybe I'll go make it somehow, for those of you who may be keeping score, maybe I'll go for, like, explain what this means in technical terms in a second. Spend a minute on it. And so what does it mean? So how do I, what does it mean in terms of spectral decomposition, this decomposition of the stack? So maybe before we go this detail, then so we wanted to spectrally decompose some space. Spectral decompose some space is the same as you think of some kind of L2 pairing. You would like to spectrally decompose that L2 pairing. And we said this L2 pairing, this is really some equivariant genus of this distribution corresponding to this L2 pairing is really some equivariant genus corresponding to a certain space. And the decomposition has nothing to do with what the genus is. The decomposition has to do with just the space. You decompose the space, and the genus just along for the ride. So anyway, so we have this decomposition, and the first part of the decomposition is summation over nilpotent elements, and that's really the summation over nilpotent elements in Langland's formula. So Langland's would like to have or an R formula, or so first of all, there's an orthogonal direct sum over nilpotent elements in the Langland's dual Lie algebra. So that's the first step. So that's second. When you take the quotient by the centralizer, you can first take the quotient by the unipotent subgroup, and then by the unipotent radical, and then by the reductive group. When you take quotient by the reductive group, what do? You just integrate, right? Because you need to extract invariance. You need to extract invariance with respect to reductive group. You integrate over maximal compact subgroup, and that integration is you have some L2 pairing. You would like to decompose it into some some pieces, and in particular there will be some continuous pieces over which you integrate, and that integration is really integration over the maximal compact subgroup of that centralizer. So that's the origin of continuous spectrum. So then in this integration there is some weight that comes to do, there's some in your geometric problem, there's some linear factors. So there is the slice, and there is a quotient by the unipotent radical. In both cases, it's just some linear object. And so then the corresponding genera give you just a function, just some weight function. And so therefore you get some weight in your spectral decomposition, you get some weight called, in spectral decomposition, it's called spectral measure. And then finally, you need to start, you need to get a function from your original function of your group. Well, you get that comes from the from integration over the Springer fibers, and that's the spectral projectors. Okay, so that sums up my discussion. There's some further directions, which maybe, since I'm out of time, maybe I'll postpone the further directions to questions, and then so maybe I'll thank you for your attention now and take questions.
Okay, well, thank you very much. Any questions? So there is at least one question: is what are the further directions?
Okay. Yeah, so we started, we made many restrictions along the lines, and more or less all of them can or should be removed in some, you know, we continue, and one way, so maybe so there's two slides here. I'll try to go through them quickly. So first of all is that we started with a group which was split, and we took the minimal parabolic. So, and all the action of, when we get that T star, we get the T star of a flag manifold, and all the kind of remaining action of the T. I mean, there was the remaining action there was action of Q by scaling the cotangent directions. But in general, if you have a general Eisenstein problem, you will have what you will have to do is you have to take the Langlands, in the Langlands dual Lie group, you take the double quotient by the parabolic, by the exponent dual parabolic, and then you take fixed points of inertia subgroup. So that would be still some flag manifolds, some number of copies of flag manifolds, but now with a non-trivial action of Frobenius. So in general, you know, the setup in this paper should be generalized by to the fact that you have flag manifold for a certain group, which is the centralizer of inertia in the Langlands dual group, and then that will have an action of Frobenius element, and then you should compute in this, do the corresponding equivalent computation in whatever case here homology. So that would be that's one direction in which this is supposed to go. And second direction is very important to go. We took this double quotient. On the one side, we took the quotient by the maximal compact subgroup. And it's very important. This is called unramified number theory. So very important to go beyond that. And as you go beyond unramified situation, you somehow allow more and more ramification. And the first thing you can do, like the first step, is you allow maybe instead of K fixed vectors, you take Ivachori fixed vectors. And then you get in the subject, which is already, you get directly to kind of issues which already been studied in Schubert calculus. And that's, you know, it's one example, one paper in which the corresponding ramifications of that theory have been already studied. And so that then you will have on top of this, so in other words, you will have on top of that stack, you have some Schubert calculus. We compute not just some genus of that T star, but rather some genus of that T star, and then coupled with some Schubert classes. And the Schubert classes, they in the Ivachori fixed case, they already been studied in this paper by well, so it's a good paper. I'm sure it's familiar to many of you. And there's it's a part of some story which is probably also familiar to many of you.